Hi, and welcome to the second lesson of Chapter 2. There's only two in this chapter, so let's jump into density curves and normal distributions. So we'll learn about a lot of different kinds of distributions in this class, and this is your very first one. So we're going to add to our skills for describing quantitative data. So we've learned the SOX acronym to help us remember to describe distributions by describing shape, outlier, center, and spread. And now we're going to get real specific. And so we have a list of steps to take when you're exploring your quantitative data, which is the first thing you do once you get a data set. If you are conducting a study and you went out and collected this data, you just want to play with it and get a feel for it overall. So the number one way to do that is to make some kind of plot. So we've explored in Chapter 1 dot plots and stem plots, and for larger data sets, histograms, or you can just do histograms for all of them, but for really small data sets, histograms are a bit much. So then you do the SOX acronym, shape, outlier, center, spread, and then a numerical summary. So you could do a 5-number summary. You could do any set of statistical measures of a data set to help you understand it. And then when data sets get really large, we even go beyond a histogram, okay? And that's what we're doing in this section. So we will turn them into density curves. And there are some rules. Density curves are functions, all right, first of all. So if this was a formal probability theory class in college, you would take it after completing multivariable calculus because the particular curve we're studying in this section, the normal distribution curve, has an equation that looks like this. This is a function of two variables. It's a function of x, but there are two constants in it, mu and sigma squared would be variance, right? And this is what the equation looks like. So x is the variable. It is a single variable curve. There's your variable x. The rest of these, pi and sigma squared, for a particular distribution, sigma squared would be a constant. So pi is a constant, sigma squared is a constant. It's used here. Mu is the mean of a data set. That would be a constant. So the only variable up here is x, but this looks ugly. And we're going to be finding areas under this curve. And so you would be doing a lot of integration if you're doing this in probability theory class. And the way that we can turn AP Stats into a class that you don't need calculus to do is with tables and or calculators that have these functions programmed in. So you will not be needing, and no one wants to see calculus on your answers on the AP exam. You will not be given credit for that because that's not how you're being taught to do this. So when we look at density curves, you are not going to have to be doing the calculus. I'm going to suggest that there are two ways to do each thing. You can do them with tables or you can do them with your calculator. And I need you to know both. I need you to be great at the calculator one. I need you to be adequate at the table use of a table because something could happen in the middle of the AP exam. Your batteries could die. You could drop your calculator. It could cease to function. And the AP graders are under no obligation to provide you with a replacement. So if your calculator dies for whatever reason in the middle of the AP exam, then you need to be able to use tables. Unfortunately, you would have no arithmetic backup unless you had brought a 4-function calculator, hint, hint. But you really need to be able to do both, okay? So let's learn what a density curve is. So this is a curve. It lies above the horizontal axis. It can also touch the x-axis. The ones we'll be looking at are asymptotic to the x-axis. Also, the area under a density curve is exactly 1. And we're going to, the comment underneath that second bullet point, we're going to draw a parallel between the area under a curve and proportions that we use for probabilities. So when we say that there is a probability of 0.75 of something happening, that's a 75% or 0.75 probability. That's going to be the area under the curve. 0.75 of the area under the curve will be shaded. So areas and proportions are going to be equivalent here, interchangeable words, basically. So take a look at this histogram for the Iowa Test of Basic Skills. This is a test they give to 8th graders here at GACS and in a lot of middle schools throughout the nation. not just in the state of Iowa, obviously. And this is the distribution of scores for 947 seventh grade students. Now notice there's a red curve imposed over it that roughly approximates the shape of the histogram. And there's some error. Any of the white spots under the curve are underestimations, and then there are some purple columns that extend outside the curve that are overestimations. And the way that we solve this discrepancy in calculus class is to take an integral to get the precise area under the curve. And once again, you don't need calculus for this class because you have charts and tables and calculator functions that will do this area calculation for you. So just know that density curves evolve from histograms, the theory behind them, and then ultimately calculus provides the clue to figuring out areas under the curves that are exact. So to describe a density curve, things that we look at when we're looking at a density curve, very specifically, not all density curves are symmetric. They can have lots of different shapes. So describing shape, outlier, center, spread, those are relevant concepts here with density curves as well. And so here are some geometric and physical ideas about how the interpretations of various statistics. So the median of a distribution of numbers that we are displaying with a density curve is the point at which the areas are equal. Half the area is above that point and half the area is below that point on the x-axis. And so if it's perfectly symmetrical, then that median is easy to find. It's when it's skewed that you can't find the median very easily. But if it's a smooth curve with one peak or one maximum point, that max value is the x-coordinate of that max value is typically the median. So a physical description of mean, some people think mean is the equal areas point. Well, if it's perfectly symmetrical, it is. But if it's not, a way to help people understand mean is the balance point. If you took a density curve and made a piece of sheet metal in the shape of the density curve and tried to balance it along its x-axis, you would have to shift it left or right from the center, or from the median, the high point of the curve, to find where it would balance. And that would be the mean. Okay, so if it's, once again, symmetrical, the density curve is symmetrical, the mean and the median are the same point. But if it's a skewed distribution, if there's a tail, the mean is going to be at that point where the curve has a peak, but the mean is going to be pulled toward the tail. And so let me give you a real life description of this. Let's say you have a class full of people that take a test and their class average is, say, a 92. And you have one guy that was late, taking the test late in test makeup, and he gets a 40, and he brings the average down to like an 82. Well, we added one data value into the data set for the guy taking the test late, and the mean goes way down. It couldn't resist that low score, so it got pulled toward the low score, which would be a tail in a distribution. The median, however, would only shift slightly, if at all. Okay, so mean values move toward the tail of a skewed distribution. So let's look at some density curves. So not all of them are symmetrical. So like I said here, here's a symmetrical density curve. We draw it, and you can see that it physically touches the x-axis. Our density curves will have points that are asymptotic, or curves that are asymptotic to the x-axis, so that the area under the curve is approximately 1, not perfectly 1. And here we have a skewed data set. And notice how the mean is closer to the tail than the median. The median's not always at the top peak. Like, it can move some with a tail, but it doesn't move as much. The mean gets yanked around a whole lot by outlying values. But the median makes conservative moves. So a density curve is an idealized version, like we turned that histogram on the previous slide into a density curve with the imposed red curve over it. It doesn't mean it perfectly describes, it's idealized, and in order for us to be able to use it for practical settings. So we want you to be familiar with the notation here. The mean of a data set is often represented with mu, okay? And when we're talking about a density curve, they call it mu. And this can be a confusing point because we use mu to represent the mean of an entire population, not just a sample. So pay attention to the context when they say mu. I don't think it's too much of a stumbling block, but I've had the occasional student struggle with that. They write the standard deviation of a density curve as sigma. Now, these are Greek letters. Typically, we use Greek letters to represent entire populations. Here, a density curve could be describing a sample. So it's the one place where we'll use Greek letters for samples. And then every other place, mu and sigma, lowercase mu and lowercase sigma, are used for population parameters. Remember, parameters are numbers that describe entire populations. The symbols for the mean of a sample are x bar, is x bar, and the symbol for the standard deviation of just a sample is s, not sigma. So Greek letters, parameters of populations, x bar and s, English letters for samples only, okay? For statistics, which are sample values. All right, so I'm making the distinction between parameters and statistics here once again, since chapter 1. All right, so normal distribution curves can have different shapes. So notice the difference here is this is a normal distribution curve. Now, not normal in the sense that some things are weird and some things are normal. This is just a name for it, okay? There could be other names, Gaussian distributions, because the mathematician Gauss was the first one to think about this. But in this class, we're going to call it a normal distribution, and it has certain characteristics. So, of course, the area under it is approximately 1, and it does lie above the x-axis entirely. It does not ever touch the x-axis, but it has these tails that have small bits of area under them going to infinity. They are completely symmetric. They have a single peak. The bell-shaped curve is in there. And there's something very specific here. Notice how they're telling you how wide the standard deviation is. And this is the width between the center of the distribution mu and the inflection point. So you used second derivatives in calculus to find inflection points in curves. And if you know where the inflection point is and you know where the center is, you can describe the curve perfectly. Notice if you go back to that equation for this curve, if you put in mu and sigma, you've got a very specific curve to graph. So if you know mu and sigma, you know everything there is to know about a curve, about a density curve, or a normal density curve anyway. So it doesn't matter whether it is wide and short, or skinny and tall. That changes with the standard deviation. So the wider spread a data set is, the bigger sigma is, the shorter and wider it is. And the smaller that sigma is, the narrower and taller that a normal distribution can be. So that's how it changes with changing values of sigma. All right. The only change it makes with changes in mu are being shifted left and right. And since we don't label a y-axis when we draw density curves, we don't have to be as concerned with that. We'll talk about what we label on the x-axis very shortly. Okay, so a normal distribution, not just any symmetrical distribution density curve, but a normal one. This is just a recap, I think, of what we said before about the center being the mean and the inflection points, which here they call the change of curvature points. So inflection points, remember, are where a curve changes concavity. And just a little bit of notation here. If you're taking notes, if you're reading a word problem and you don't want to read it 6 times and it tells you that a distribution is normal and it tells you what the mean is, it tells you what the standard deviation is, you can put in with parentheses mu in front and standard deviation in back. If it's not normal but you're being given the mean and standard deviation of a distribution, just leave off the capital N. So there's some shorthand in your note taking that you can take advantage of. All right. So the importance and why we start with this, clearly the first version of something you learn is either the simplest or the most necessary basic founding idea that is going to be used as an underlying concept and a means of understanding more complicated stuff later on. So probably the most important distribution here. And normal distributions are usually found naturally in a lot of different situations, but they are the result of chance outcomes, okay? There are some chance outcomes that come to mind immediately, like the distribution for rolling 2 dice is very much a normal distribution. But also chance outcomes include things like asking people's incomes, or ask people how many times a week that they text other people, things like that. Those are chance outcomes because one person's answer to that doesn't really affect another person's answer to that in a large population. So these distributions pop up naturally in chance outcomes. And later on, we'll learn other inference procedures. Well, we're not doing inference procedures yet, but if we want to infer something about a set of data, if we want to go beyond the data and use it to predict stuff, that sort of thing, lots of those procedures are based on a bell-shaped symmetrical distribution like the normal distribution. Okay, so here is time for math problems, basically, which is only about 20 to 30% of this course, really. The rest is conceptual knowledge. And so here's a very typical normal curve. And notice it now has labels on the x-axis. Well, these labels are z-scores, okay? So 0 is the mean of a standardized normal distribution, and the standard deviation is 1, and that is the defining feature of a standard normal distribution. So if I take a set of data that's normally distributed, meaning it has a perfect bell-shaped distribution, or approximately symmetric bell-shaped distribution, and standardize everything. Take every data point in the whole data set and turn it into a z-score. Remember how to do that? You take your data point, you subtract the mean, you get that deviation from the mean, you divide it by the standard deviation, and you get a z-score. So we take every data point in a data set, convert them all to z-scores, and that is a standard normal distribution. Okay, so you can have a normal distribution with a mean that's not 0 and a standard deviation that's not 1, but once you convert them all to z-scores, it's now been standardized. All right, so we want to take note of the data points, the z-scores of 1, 2, and 3, and the data points where those fall, meaning 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean, and then 1, 2, and 3 standard deviations below the mean. So those z-scores are very meaningful. Notice that by the time you get out to 3 or -3, there's not much left under the curve, these little bitty pieces under the tail. So we really don't have to go all the way to 4, but remember this curve, the purple curve on either end, is an asymptote. So z technically goes up to infinity and down to -infinity. It just doesn't have much area under the extreme ends of the tails. Okay, so in a normally distributed set of data, here is, they call it the 68, 95, 99.7 rule. It's also called the empirical rule, and you'll see it described that way in the book, and you'll hear me use it, and they'll use it on the AP exam, so also know that name of this rule, the empirical rule. Says that the area under this curve within 1 sigma, or 1 standard deviation of mu, is 68%. So that's 1 above and 1 below. When it says within 1, that's 1 above and 1 below. So between, let me get all these in here, between this line at -1 standard deviation and this one at +1 standard deviation, all of this light shaded area, that constitutes 68% of the area under that curve. And then you move to 2 standard deviations above and below, so that's between -2 and +2. That constitutes 95% of the data. So that's this middle part, and then those are the light green parts. So all of it from here to here is 95% of the data. And so you could figure out, if 68 is the middle, the difference between 95 and 68 is 27. If you cut 27 in half, then each of the light green portions is 13.5% of the area under the curve, or 0.135. So then finally, 3 standard deviations above and below the mean, that constitutes almost all the data under the curve, 99.7%, which only leaves 0.3% for these little tiny tails outside, beyond 3 standard deviations above or below the mean. So 0.3% cut in half means each of these little tails is 0.15% of the area under the whole curve. So these are numbers that you should know by heart. It's not on a formula sheet anywhere. All right, so the standard normal distribution, Talked about that a bit. Here's their notation: N for normal, 0 for mean, 1 for standard deviation. The z-score is also, formula is also not given on a table anywhere. Okay, so speaking of tables, I need to take you with me to the class website and show you the Welcome to AP Statistics course documents. Since our first sync session, I have added the formulas and tables sheet. Now you get this copy of this document, which since we're in a virtual school, you have to bring to the test with you. You get this for every test. So I suggest you go ahead and print a copy because you're going to want it not to be on your screen when you're taking your test on your screen in a lockdown browser or what have you. You just going to want a physical copy of this. So print it and keep a copy with you. And so we're going to look at some of the pages that are on this. If you click here, you have to hover over that spot, by the way, for that to show up. If you click there, let me show you that one more time. Hover over it down here and click this item, and it opens the document up as a PDF, and you can save it to your desktop. So it's 10 pages long. We will not use very much of it for the first test, but every chapter will add to what we know and use from this. And so right now, X bar is the mean of a data set. SX, there's our standard deviation formula, and that's all we've learned so far. Okay, we won't learn these next ones until chapter 3, and some of them we won't have to know by. It's very, very rare for us to use this one, but they included it on there anyway, just in case. And like this is chapter 6, and this is chapter 7. So this up here is chapter 5. We won't be using a lot of this until we get substantially up in the curriculum. Okay, so you can ignore all these for now. And fortunately, you don't have to memorize any of them because you can use this for the AP exam as well. So go ahead and print it. But what we're going to look at is Table A, Standard Normal Probabilities. So here's our standard normal curve. They're showing you that z-scores are on the x-axis here and that the probabilities given in this table, see all the numbers, probabilities have to be numbers between 0 and 1, right? If we don't express them as a percent, but a decimal, they have to be between 0 and 1. And so the word probability here is pointing to a shaded area to the left of a z-score. This probability, this shading of the area under the curve and the probability numbers are analogous. Okay, so I'm going to show you how to use this in this section, and you're going to want to have this table with you to do problems for most of the rest of the curriculum in the class. Okay, so notice how they describe it, a table of areas under the standard normal curve. So before they said probabilities, this says areas, and remember, if you recall, I said we're going to use those interchangeably, okay, because the area under the curve is 1. Any partially shaded area would have to be a number between 0 and 1, which is just like a proportion. So area and proportion are the same thing, okay? The other specific issue, is that the area under the curve to the left of z. So that's why the shading is on the left, to remind you that these areas down here are areas to the left of a z value. So we're going to go over how to read this table. So we want to find the proportion of observations in our data set from a standard normal distribution less than 0.81. So this is how we write this, and I expect to see these in questions in your homework when you're asked to find these proportions. I need to see probability notation. I'm sorry, I keep hitting that on my mouse. So the probability that z is less than 0.81, that the shading under the curve is less than 81% of the area of the curve, is written with this P parenthesis notation. P of z is less than 0.81. So this is the probability that z is less than 0.81. And then we go to the table. Okay, so I'm going to do it over on the big table, 0.81. So we're going to look in the table for the number closest to 0.81. And notice these numbers are tiny. We'll look at the z-scores. These are negative. So negative z-scores would be on the left half of the curve. The areas, the farther left you go, the lower the z's, the smaller the areas. So 0.81 is really a positive amount, and more than half of the area underneath. So the middle point, 50% area point, is exactly in the middle. So 0.81 is above halfway point. So negative z-scores aren't relevant here. So that's the first 2 pages are negative z-scores. Second 2 pages kicks in with half the area, 0.5 right there. So I'm going to go find 0.81. So 0.81, the closest value. So here we've got below 0.81, here we've got above 0.81. This is 6 10,000ths above, this is 22 10,000ths below. So right here, 0.8106 is the closest value to 0.81. We need to read the z-score off of this, okay? Okay, wait a minute. Let me see real quick. And I need to okay. How do I put this back on? Okay, so the way that we read this table is we're going to go over to our score. Now remember, z is less than 0.81, so we've got to find z of 0.81 on here. So if you'll notice, this table, this column is z-scores with 1 decimal place. So 0.8 is right here. The second decimal place is along this row. So 0.81 would have 0.8 on the left-hand column, and 0.01 up here for the second decimal place, and where that row and column meet is 0.7910. I'm trying to highlight just that one number. 0.7910 would be our area where z is 0.81. So that's what they're showing you in this little bitty version of the table over here, 0.801, okay, where that row and that column meet gives you your area under the curve, the probability that a randomly chosen data point would be in the shaded area under that distribution curve. All right. So here's the steps. Now, showing your work is that probability expression P of z is less than 0.81 equals 0.7910, and I would always tell you to put using table A if you use table A. If you don't use table A, you're going to use your calculator. So I'm going to show you where that is. If you go here, we have distributions. See how distr is the second function on the vars button. If you hit second vars, brings up a list of distributions, and you see your normal PDF and normal CDF. Now, we will almost never use normal PDF. It's not that it's useless, we just don't have a frequent use for it in this class. We will almost always use the normal CDF. So I'm going to tell you to go to 2. And if you have a more recent model calculator, you have this nice wizard to help you. If not, I'll show you what you do. And you might think about getting an upgraded one before you go to college. The sooner the better, frankly. Okay, the lower limit, since we're doing is less than z, the lower limit is on the left side, which is negative infinity. And notice how they've got scientific notation here, -1 times 10 to the 99th power. Well, that's not infinity, negative infinity, but it's really close. You could also just do like -9999999. Okay, and in fact, don't make the same mistake I just made. Don't use minus for negative, use this for negative. 9999. You do a bunch of 9s. That's the same thing. It's not technically the same number, but it's a z-score this low is really, really low, okay? The upper level was the 0.81, and we wanted less than 0.81, and then it's standardized, so mean is 0 and sigma, standard deviation, is 1. We don't have to change those. Hit paste. So it puts the command in for you. If you arrow left, you can see that it's the normal CDF command. All right, if you don't have a wizard, you're going to have to do, I'm going to hit enter, and then it'll give you that 0.7910 that we got out of the table before. Sometimes it'll be slightly different than the table because this is more precise than the table. Remember, the table isn't a continuous list of values, it's discrete. So I like the calculator because it's easier, it's less work, but the way you show your work with a calculator is you have to actually write this command in. You have to write normal CDF, parentheses, -99999, 0.81, 0, and 1, all separated with commas. Then you have to label each thing. So what you would label, you would draw a little arrow and you would put lower limit here. And for the second number, you would put upper limit. Then you would put mu and you would put sigma, and you can use the Greek letters there. You don't have to write out the words. You have to label each item in the parentheses, put the entire command in your work in order to use the calculator, and then you wouldn't have to say, quote, using table A. So technically using the table is less writing. It's your preference which you want to use. I recommend the calculator. All right, please don't learn to use the table only and never use the calculator though. I need you to learn both. So that's how you do it in the calculator and what you have to show in your work on an FRQ. Notice how it says use the normal CDF command and label each of the inputs. All right. Finally, answer the question. Okay. So the answer is not, the answer to the probability that Z is less than 8.1 is 0.7910. But when there's a context for the question, this is the single biggest mistake that kills AP exam scores out of all of them. People will leave the answer as 0.7910. When there's a context to the question, now, in our question they gave us, we can go back and peek at it. It just said, find the proportion of observations from the standard normal distribution that are less than 0.10 or 0.81. So the answer was a proportion, which 0.7910 is a proportion, okay? But if there's a context to the question, find the percentage of students that scored lower than 81st percentile. Your answer wouldn't be 0.7910, it would be 79.1% of students scored below 81st percentile. So you would put the context in and you would answer the question. So don't just leave some number at the end of a calculation as your answer when it was a word problem. You must phrase your answer in a sentence with the relevant numbers for the answer or you will lose credit. Please write that down in a note somewhere. You'll lose credit on my tests for it too. All right. When it comes to those judgment calls, remember in the first sync session, I described AP grading of the FRQs, and you can get 4 points total. That's a perfect score on a single FRQ question. But sometimes you come up with scores like 3.5 or 2.5, and then it's at the AP grader's discretion whether to push you up or down. I told you they more frequently round down than up. And if you give reasons for them to round up, then you'll get better scores. So what are reasons for graders to round up? They would be properly wording sentences to express the answers to your questions in context. The other thing that you can do to get those half points rounded up, and it happens often enough that you need to know this, is to draw the normal curve. Any question that involves a normal curve, table A, or normal CDF, you need to draw a picture, okay? You need to draw that density curve, put a label where Z is, whether it's above the middle or below the middle, and shade the relevant portion under the curve. Even in your homework that you turn in to me, especially on the AP exam and the unit tests, okay? So make sure that you are being thorough. So here they are both in the same question. Draw the picture of the normal curve, answer the question in a sentence. If you are the student who abbreviates and shows as little work as possible, you will kill your AP exam score right there if you don't do these things. All right? Finally, sometimes we need to know if a set of data is approximately normal. Okay, there is a particular plot that will help you with this, and you can produce this plot on your calculator. So I'm going to show you a normal probability plot on your calculator. All right, before class, or before the recording, I entered a list of data into the calculator here under list 1. All right, and I need to know if this set of data is normal, so I am going to do a statistical plot. So here's how we do that. Once you've entered your data into the list, which you had to do in chapter 1, and remember there's a little video in the calculator stuff section on your online course that if you need to be refreshed on how to put data in, please go watch that like minute-and-a-half long video. So I put my data in, and I'm going to go and turn on a statistical plot. So maybe I should hit clear. All right, see this again, a statistical plot. Well, you can quit this and get out of this and go back to the main screen. But if you hit second, y equals, that will get you stat plot, and there it is. And you can put in up to 3 at a time, excuse me. You can turn them all off together or all on together. We're just going to be working with one at a time in this class. So I'll do the first one, and you see how the cursor's blinking on. If I hit enter, it will highlight on, and when I arrow down, on will stay highlighted. So here's all the statistical plots. This is a scatter plot, which is a chapter 3 and chapter 12 idea. This is a line graph, which we really don't use in this class. This is a histogram, and we had a video posted in the calculator stuff section about how to do these. This is a box plot with outliers identified, and this is a box plot with outliers included. And this is our normal probability plot. So arrow all the way over here, hit enter, and then arrow down. And I put my list under list 1. Notice that you could insert list 1, list 2, list 3 with the blue second key and the buttons 1 through 6. So if you decided that you needed your data in L1 and you didn't want to delete it, you can put your list in some other list, or put your data in some other list and put a different list here. All right. We always want the data to be on the x-axis in a normal probability plot. If you do it the other way around, you'll read it backwards. So just leave the data axis as the x-axis and put whatever marker you want on it. I like the first one best. You can change colors if you have the computer that does that. So now you can hit graph, but your computer will, or your printer, excuse me, your calculator will like it better if you hit zoom stat. So zoom 9, it knows how to mark the axes if you do that. If you just hit graph, sometimes it looks funny. Now, this set of data, if it were normal or approximately normal, would follow the pattern of a straight line. Okay? Doesn't matter how steep, doesn't matter where in this graph, it's straight, but a straight line. So this doesn't look particularly straight to me. Points that fall outside the pattern of a straight line typically would be outliers. So we're not actually allowed to eyeball a line of best fit. And we'll learn that in chapter 3, how to do that precisely. And you've probably done that in a math class in high school before. But I wanted us to see different normal probability plots. I need to find my browser. Here we go. And here's a bunch of different normal probability plots. So like this one looks like the data conforms to a straight line pretty well. So we would say this data set is approximately normal. This one, on the other hand, is completely not normal. This one down here is completely not normal. They are not straight lines, and they don't look anything close to straight lines, whereas this one is almost perfectly a straight line. Here's one with an obvious outlier up at the top. So normal probability plots. Now, we can talk about why they look like straight lines very briefly. I like this one for that example. On the x-axis are the data points, and on the y-axis are the equivalent z-scores. So when you standardized all the data, we plotted them in a 2-coordinate graph where x is the data point and y is the z-score. And that will help you understand why, if we have z-scores being represented from -3 to +3 pretty well, and all the points lie along the line, that means we have data distributed so that there's a peak in the middle and tails at the end. And so when we have outliers, that means we have skewness. Now, it's only one outlier, so I'm still willing to bet that you would call this approximately normal, okay? But something like this, not anywhere near normal, okay? So that's how you assess the normality of a data set, and that's a skill we're going to use very much toward the end of the class and just a little bit here. All right, that is everything you need in this section. Thanks for listening. Bye.